Congratulations on your successful completion of part 1. In part 2, we are going to talk about the statistical model. So, creating a statistical model. Of course, let's go back to our example. A researcher is studying the relationship between the decrease in a person's blood pressure and personal and environmental variables to which they are exposed. Now, knowledge from observational studies and laboratory findings suggests that the decrease in a person's blood pressure is related to their sex, age, and a drug believed to reduce blood pressure. Let's build a statistical model for the decrease in blood pressure. Now, statistical models are math functions, and math functions are relationships between variables. Now, on the left side of our equal sign is going to be our dependent variable, also known as the response variable, or in epidemiology, as the outcome. And on the right side of the equal sign is going to be the independent variables, also known as the explanatory variables, or in epidemiology, once again, as the predictors. Now, the most basic, the most simple model would be to have a constant as your predictor, if you wish. And you can imagine that if you have a single constant to predict the values you would find in your dependent variable, your outcome, there's going to be some error. It's not going to be right most of the time. And so what we've done here is we've listed, let me just get my pointer, we've listed here the dependent variable, here the constant, and here we're describing your error. Now J is of course for each instance of your dependent variable. And so if you rearrange this, you can just see very simply that your error is equal to the value, the value of your dependent variable minus this constant k. Now the sum of squares, you guys are all pros. The sum of squares is going to be the difference between this difference here, so basically your error squared, right? And that's your sum of squares that you can use for your calculations. Now, interestingly, the sum of squared deviations about k is at a minimum if k is equal to the sample mean, in this case, of the decrease in blood pressure. And it's for this reason that it's called, or the sample mean is called the least squares estimate of k. Now, interestingly, this, or so when you predict an outcome when using the sample mean, that's probably the most basic model you can put together. Let's look a little closer at this least squares estimate of k. So in this model, we are still predicting the decrease in blood pressure. We have chosen our constant k to be the mean of the population for the decrease in blood pressure. Inevitably, since this is a constant, there's going to be some error associated with the prediction of the dependent variable. And this error is going to be equal to the value of the dependent variable minus the mean of the population. But because we are working with a sample now, not the population, we're going to rename the error residual. And in this case, the residual is going to be the value of the dependent variable minus the mean of the sample. That makes sense, correct? If we then look at our sums of squares here on the top, it's nothing new. It is the value of the dependent variable minus the mean of the sample squared, and it's the sum of them. And to get our variance, we divide by n minus 1. This is, once again, as we've seen previously, an unbiased estimator of the variance that is in the formula of the Gaussian probability density function. Nothing new, but we're just starting to tie this in to the model, the statistical model. All right, now most of you immediately were thinking, why would I ever predict my outcome with the mean of the sample? I mean, sure, it's the most basic model, but come on, we can do better than that. And you're right, we can use the straight line model. So in this case, what we've done, we have the same dependent variable, but what we've done is we've added a little more to the right side of the equal sign. So what we've added is beta naught, which is your intercept with the y-axis of your straight line, beta 1, which is your coefficient or parameter estimate for age. So now we're adding age as a predictor to the model. And then inevitably, this is not going to be perfect, and so there's some error associated with that prediction. So that you guys understand, we've just seen it in the previous slides. So then if you flip it over, once again, you get error is just simply equal to the value of your dependent variable minus beta naught minus beta 1 times age, which is the coefficient for age. And this is for every instance in your dependent variable. All right, in this straight line model, we now have two parameters that we're dealing with, beta naught and beta 1. It turns out that beta naught, which I've already told you, is the intercept, and beta 1 is the slope. And you can see here, I'm just giving you the equations for the least squares estimates of the intercept here and the slope of your straight line. Now, what's important to observe is that the residual, and you remember we called residual the error when working with a sample, right? And so the residual in this case, which makes sense, is the observed minus the predicted. That makes sense because you're looking at the difference between what you predicted with what you observe. And the observed minus the predicted, or the residual, is equal to your dependent variable value minus the other side of the equation, which is your intercept, beta naught, minus your slope, beta 1, times age. Now, when you look at your sample variance, just as we did in the previous slide, here we had the value minus the mean squared divided by n minus 1. But in this case, we're using the residual. Once again, it's still the residual, but in this case, we have two parameters in the residual. And this is what the residual is equal to. And we're going to put it in here and square it. And this time we divide it by n minus 2 because there are two parameters in our residual that are being estimated. And this, once again, is an unbiased estimator of the variance that, again, is in the formula of the Gaussian probability density function. Now, before you get too stressed about all the math and the equations, just remember that you are not required to do any of these calculations by hand. We're just showing this to you so that you can, to help you to understand how these statistical models are built. Now, you'll remember in the previous slide when we were doing a straight line fit, we had a single predictor, which was age. Now, in the multiple linear regression, all we're doing is we're adding more predictors. So you'll see here now we've added drug, we've added sex, and we've kept age. Now, in this way of writing the equation, because this is basically the truth, right? So this is your decrease in blood pressure as observed in your dependent variable. You have to add on the right side of the equation error, right? Because it's not going to be perfect. The prediction will not be perfect. But interestingly, if you change how you write this out, if you say that what you show here on the left side of the equal sign is actually the predicted value, so not what you've observed, but actually what you've predicted, and you put a little hat on it to say this is prediction, then what happens is on the right side of the equation is your predicted, the estimates of your predictors. So these are the estimates, beta 1, beta 2, beta 3, of your predictors, which is going to be drug, sex, and age. And therefore, in this case, the error term is not needed because this is the predicted value, not the observed value. This is just a little subtlety of how you write your models. But it's also to keep you, help you remember the difference between an observed value and a predicted value. Now in this case, because we've added another 2 predictors to our equation, drug and sex, when you calculate the residual, which as we said previously is the observed value minus the predicted value, when you calculate your sample variance, in this case, your residual is estimating how many? 1, 2, 3, 4 parameters. And for that reason, you divide by n minus 4. Let's cover one more possible scenario with this multiple linear regression model. What if the distribution of drug, so meaning successfully decrease the blood pressure on the drug versus not on the drug, is different with each level of sex? So in this case, there's only 2 levels, which would be male and female. This means that drug and sex are associated. There's a relationship between the two, and we call this interaction. And what it can be when you have a drug and sex interaction in this case would be that the size and possibly also the sign of the drug effect is different among males and females. If this is the case, you're going to want to test that interaction, and to do that, you need to include in it, let me get my laser pointer again, sorry about that, you're going to want to include another term, and this is going to be the interaction term, drug times sex, with its parameter estimate. And in this case then, your predicted decrease in blood pressure is going to be equal to the intercept, drug, sex, the interaction of drug and sex, and age. So then, of course, we now have 1, 2, 3, 4, 5 parameter estimates. So in our sample variance, we're going to divide by n minus 5. So this is probably the most complicated model that we're going to teach in this course. I just wanted to get through all the models in one go. And then we're going to show you now in the following lectures how to actually apply these models to a data set in order to test a comparison or a prediction. So you've seen in the previous slides all of these equations, these model equations that have these betas. And so I'm sure you've been all thinking, what values should these betas have in order to minimize the error term that's in that model? So minimize the error. Now, all statistical programs produce values for these unknown betas, also known as parameter estimates, so that the variation among the error terms is minimized. So how is this variation measured? Something you know well already. It's a statistic called the variance. Now, values given to the beta constants will be such that the sum of the error terms is 0 and their variance is minimized. Now, is this variance an estimate of the variance that is in the Gaussian probability model? Yes, of course. Okay, let's see an example. Now you've seen this data set before. It is the reaction time data set from part 1, where we are identifying a green or red object on the screen, and we record the time it takes for you to click on it using a mouse. Now, the way we've received or we've ordered this data is one line of data for each subject, and this is typically how you would organize or receive the data set. Our input is going to define the variables. We have color, which is a character variable as defined by the $sign. The name of the participant, same thing. Your ID is a numeric variable for the ID, and then your reaction time. Okay, here's the code we're going to use. Now, some of you might be thinking, what happened to proc t-test? And you're right. That's what we used in part 1. But here in part 2, we're talking about the statistical model. And so we're choosing to use another procedure called GLM, General Linear Model. And the reason we are is because you'll see that it's much more versatile than the t-test. We're going to do the analysis 2 ways. The first way, assuming a completely randomized design. And the second way, assuming a randomized block design. Now the difference is that in the completely randomized design, there is one person for each measure. Whereas in the randomized block design, each participant, each person, repeats for both red and green. That's the difference. Now you'll see in the code, because in the completely randomized design, there is one participant per measure, we only have the class variable color as an independent variable, which is our group variable, with 2 levels, red and green. In the randomized block design, we now add another variable, also an independent variable, but this one is ID, which is our block. Each person actually turns out to be a block, and we include that in the model. The LS mean stands for least square means, and all we're asking for is for color, please do a t-test. Give us the results of the t-test, the probability of the t-test, the standard error, and the confidence limits. That's what we're asking for. Now, in this case, we chose to use the ID variable, but we could have used the name variable, but then we would have had to have added it to the class statement up here, or here for that matter, and it would have given us the same results, even though ID is a numeric variable and name is a nominal variable. Okay, so here's the results for the completely randomized design analysis. The first thing you'll note down here is that the p-value, 0.5323, is exactly the same as the p-value we got when we performed the t-test on the same data set back in part 1. Now, the other thing that I would like to point out is the F statistic, so the value from the F test. If you take the square root of it, it's equal to 0.65, and this is equal to the t statistic that we had when we did the t-test. So the F statistic is equal to the t statistic squared. This is just an interesting relationship between the two tests. The other thing I wanted to point out is the R square here. Now, often you guys, look for the R square, which is when you take the percentage. So in this case, it's 0.05. So the percentage would be 5% of the variability. So that means that the model accounts for 5% of the variability that exists in the dependent variable. So you'll note that 5% is incredibly low. Like, wow, that's pretty useless. And it's not surprising because it's not even statistically significant. So the model is not even statistically significant. Now, if you remember, we asked for the t-test to be performed between the levels of the grouping variable color. In this case, there's only 2 levels, so it's a very simple comparison. And it was the LS means statement that we used, and therefore here we go. LS, least square means, is given to us. Here's the t value from the t statistic. And as you remember from the previous slide, it's 0.65. There's your p-value. Nothing has changed. But what this also gives you is your confidence limits. Now, interestingly, it gives you the difference as well, by the way. But if you'll note, in the confidence limits, this interval includes 0. So that makes sense. As we've always been saying, if the confidence limit includes, or interval includes 0, then your p-value is going to be greater than 0.05. So this confirms everything we did using proc t-test. So what if we were to assume a randomized block design? So when we do the analysis this way, the first thing I'm going to point out is the R-square. It's now 97%, which is indicative of a very good fit. Your model is a very good fit for the data for predicting your dependent variable. Now, interestingly, the R-square, how you calculate it, I just want to show you, is that you take the sums of squares for the model and you divide it by the total sums of squares, and that gives you your R-square. Now, if you want to look and see if there is a significant difference in reaction time between the colors, you would come down to color in the type 3 sums of squares. Always look at the type 3 sums of squares. We'll talk about that a little bit later, but this is the one you will always exclusively look at. And look at the p-value here, and it's 0.0487, and that's the same as when we did the matched pairs design t-test. We got the same p-value. But now the additional information we have is an R-square for your model, which gives you a fit, a model fit. How much variability is being accounted for in your dependent variable by the model? Once again, looking at the least square means, no surprise, here's your p-value. We just saw it on the previous screen. It's just confirming. And then once again, if you look at your confidence interval, it does not contain 0. So now we're in sync here between your p-value being less than 0.05 and your 95% confidence interval not containing 0. So we've just shown that we can analyze the same data set using 2 procedures and getting the same results. So what's the advantage of using GLM, the general linear model procedure, over the t-test procedure? Well, let's just say we have another analysis to perform. In this case, it's comparing 2 drugs. So your reaction time when you're on one drug and versus the reaction time when you're on another drug. And we also know that sex, the reaction of the drug, is different depending on your sex. And it's possible that your age and weight will also affect your reaction time when on that drug. So when using ProcGLM, you are able to include all of those variables in the model at the same time and perform your analysis to test whether or not the reaction time differs between the 2 levels of drug, so drug A versus drug B, as opposed to doing a t-test where you can only test 2 levels of a class variable at once and you cannot adjust for any other variables in the model at the same time. That is a big advantage for using ProcGLM. So to summarize, if the reaction time variable is the outcome variable, your primary question is, does the variable drug predict outcome? In other words, are the drug and outcome variables associated? Now, if sex, age, and weight predict outcome, including them reduces the residual variance, which increases R² and reduces their p-values. If the effect of drug is greater for males than females, then this is what we call interaction. And all of this can be analyzed using proc-GLM. Now, if the predictor variables sex, age, and weight are also associated with the drug variable, so your group variable that you're interested in, then excluding them produces biased estimates of the drug effect. And then they are called confounders. The product variable drug and sex is called the interaction, and if it is large, it means that the size of the drug effect is different for males and females. Okay, time for a little cartoon. So here are two cavemen. One of them has a rock and a feather in his hand, and he says, if I drop both of these, which do you think will land first? The other caveman, of course, says, I think the rock will hit first. So the other caveman drops his feather, waits and waits and waits and waits until it hits the ground, and then he drops the rock. So, of course, this isn't what the other caveman was expecting. So in the cartoon, the loser assumed his friend would let go of the rock and feather at the same time. But that was not part of the bet, and that's the funny bit. Now, in many studies, researchers may mistakenly think that the comparison was fair and valid. For example, in a study, the proportion of males in the exposed and unexposed groups may be quite different. And if males are at higher risk of disease, the comparison would be biased. So what we're going to start to look at is that depending on your design, you are going to have to structure your analysis in order to account for the design so that your results are not biased. We're also going to start talking about the fun of accounting for confounding variables. So here, for instance, you've seen two of them already. So there are three designs we can have a look at: completely randomized design, the randomized block design, and the split plot design. Now, in terms of a treatment layout, you can have a one-way treatment layout, and you can have a 2x2 factorial treatment layout that we'll also look at. Now, in terms of outcome variable, we will go through most of these outcome variables in this course. So continuous, of course, something like blood pressure and serum cholesterol. The binary variable, which is yes, no, so a death, yes, no, cure, yes, no. The count variable, which is like, for instance, the number of deaths, number of falls. We will only touch on count variable a little bit in this course. And then finally, survival time, which would be like time to death or time to cure. And we will cover survival analysis or the introduction to survival analysis in the last lecture. Okay, that brings us to the end of lecture 1 in part 2. And next up in lecture 2 will be study design.